Hello everyone. Today we are embarking on humanity's most profound scientific quest, uncovering the signs of alien life across the cosmos, using the most advanced eye we have ever sent into space, the James Webb Space Telescope. For centuries we have stared up at the night sky and wondered if we are alone. For decades, telescopes like Hubble and Kepler gave us hints, mapping thousands of exoplanets and revealing that our galaxy is teeming with worlds beyond our solar system. But none of them could do what Webb does: detect the faint, invisible, chemical fingerprints that signal life might exist on a distant rock or ocean world, hurtling through the blackness of space. This is not just astronomy, this is the story of us reaching out to touch the unknown, to answer a question that has defined human curiosity since the first ancient astronomer looked upward: are we truly alone? To understand how Webb hunts for alien life, we first must understand what a biosignature is. A biosignature is any substance or pattern of substances that provides strong scientific evidence of past or present life. On Earth, our atmosphere is a living billboard. Plants pump out oxygen through photosynthesis. Microbes in swamps, oceans, and even the guts of animals release methane. Algae in our oceans release dimethyl sulfide, a gas with almost no non-biological source on our planet. These gases do not exist by random chance. They are byproducts of life, relentless chemical activity. For decades, scientists have dreamed of detecting these same gases on planets light years away. But until Webb, that dream was impossible, because those critical chemical signatures shine brightest in the infrared spectrum, a range of light completely blocked by Earth's atmosphere and invisible to older telescopes. Webb's superpower is its unmatched infrared vision. Its 18 hexagonal, gold-plated beryllium mirrors are cooled to temperatures colder than the coldest depths of space, shielded by a giant 5-layer sunshield, the size of a tennis court, blocking heat from the sun, Earth, and Moon that would drown out faint cosmic signals. This design lets Webb detect infrared light with a precision no previous mission has ever achieved. It can pick up chemical traces as faint as 1 part per million, like finding a single drop of water in an entire swimming pool. And it is this precision that lets it perform the cosmic magic, that is, transmission spectroscopy, the core method Webb uses to study exoplanet atmospheres and hunt for life. Let me break down transmission spectroscopy in simple visual terms, the way you would see it unfold in the cosmos. Imagine a distant star, calm and bright. Orbiting around it is an exoplanet, maybe a rocky world in the star's habitable zone, the narrow band, where temperatures are mild enough for liquid water to exist on the surface, the universal solvent we believe life needs to begin. Every so often, that planet crosses directly between its star and Webb's gaze. This is called a transit. As the planet transits, most of the star's light is blocked, but a tiny sliver of that starlight passes through the thin upper edge of the planet's atmosphere before traveling the millions or billions of miles to reach Webb's detectors. Every molecule in that atmosphere, water vapor, carbon dioxide, oxygen, methane, absorbs very specific wavelengths of infrared light, like a unique barcode or a fingerprint no other molecule can copy. Oxygen and ozone absorb light at near-infrared wavelengths. Methane shows its footprint in the mid-infrared. Dimethyl sulfide has a distinct signature that Webb's MIRI instrument is built to pick up. Webb first measures the spectrum of the star alone, then measures the spectrum during transit, and subtracts one from the other. The gaps and dips that remain are the atmospheric fingerprints Webb is built to read. Those gaps tell scientists exactly which gases are present, in what concentrations, and even how they are distributed through the planet's skies. But here is the critical part: scientists never skip. No single gas proves life exists. Oxygen alone could come from non-biological processes, like the breakdown of water vapor by intense stellar radiation. Methane alone could come from volcanoes or hydrothermal vents, just as it does in some places on Earth, without any life involved. What makes a signal truly promising is a state of chemical disequilibrium, a mix of gases that cannot coexist for long, unless something is constantly replenishing them, and that something is almost certainly life. On Earth, oxygen is highly reactive, and methane is easily broken down. They should destroy each other quickly. Yet they stay present together, because life is constantly producing both. If Webb finds oxygen or ozone paired with methane in an exoplanet atmosphere at levels far beyond what geology or chemistry alone can explain, that is one of the strongest red flags for alien life we can hope to detect. Webb is not just pointing randomly at stars. It is targeting the most promising worlds we have discovered so far. One of its top priorities is the TRAPPIST-1 system 40 light-years away, a miniature solar system with 7 Earth-sized rocky planets, 3 of which orbit firmly within the star as habitable zone. These planets are small, cool, and orbit a tiny red dwarf star, making their transits frequent and their atmospheric signals easier for Webb to catch. Webb has already begun scanning these worlds, looking for signs of thick atmospheres, water vapor, and the gas combinations that hint at habitability and possibly life. Another groundbreaking target is K2-18b, a Hycean world, a planet with a global ocean under a thick hydrogen-rich atmosphere, 124 light-years from Earth. In 2025, Webb made headlines around the world when it detected strong signs of dimethyl sulfide, or DMS, in K2-18b's atmosphere. On Earth, DMS is produced almost entirely by marine plankton. There is almost no geological process that makes it in large amounts. Paired with detections of methane and carbon dioxide, this finding became the strongest evidence yet of potential biological activity outside our solar system. Scientists are cautious. They need repeated observations to rule out instrument noise or unusual chemistry. But the signal is clear, consistent, and exactly the kind of clue Webb was built to find. Webb's suite of instruments makes this level of detection possible. NIRSpec and NIRISes cover the near-infrared, capturing light from water vapor and oxygen. MIRI, the mid-infrared instrument, reaches longer wavelengths to lock onto methane DMS and other heavy molecules that are key biosignatures. Together, they create a full picture of a planet atmosphere that no single instrument could provide. This is not just technology. It is a global collaboration between NASA, the European Space Agency, and the Canadian Space Agency. Thousands of scientists and engineers working across decades to turn a dream into a machine that can read the sky's most secret messages. We must also talk about the challenges Webb faces, because great science always balances hope with rigor. Some exoplanets are shrouded in high clouds or hazes that block their atmospheric signatures, hiding their true chemistry from our view. Stellar activity, flares, sunspots, and stellar wind can pollute spectra and create false signals that mimic biosignatures. Small, Earth-sized planets create extremely faint transit signals. A planet like Earth blocks just 0.008% of its star's light during transit, compared to 1% for Jupiter, making those signals incredibly hard to measure. Webb pushes past these barriers with extreme precision, but scientists still run dozens of models and cross-check every result to avoid jumping to conclusions. We do not claim life until we have proof that holds up to every test. What makes Webb's mission so deeply meaningful is that it connects to every human being who has ever felt small under the stars. It is not just about finding microbes on a distant rock. It is about understanding our place in a universe that contains trillions of galaxies, each with trillions of stars and planets. For thousands of years we thought Earth was unique, the center of everything. Now, we know we are one tiny world in the cosmic ocean. Webb is our boat, our compass, our way to sail that ocean and look for other sparks of life. It also changes how we define life itself. We used to think life had to be like Earth, carbon-based, water-dependent, breathing oxygen, or releasing methane. But Webb is teaching us to think bigger. Hycean worlds, like K2-18b, are nothing like Earth, hotter, thicker atmospheres, global oceans under heavy pressure, but they might host microbial life that thrives in conditions we would find deadly. Webb's observations are expanding our list of possible biosignatures, including methyl halides and other gases produced by exotic lifeforms, forcing us to rewrite the textbooks on what habitable really means. Every time Webb turns its gaze to a new exoplanet, every time it uncovers a new gas in a distant atmosphere, it writes a new page in the story of cosmic exploration. We are no longer just counting planets. We are characterizing them, measuring their skies, tasting their air, and listening for the quiet hum of life. Webb cannot take a photo of a green alien or an alien forest. It cannot see creatures walking on a surface. But it can do something just as profound. It can detect the breath of alien life, the chemical byproducts that no lifeless world can sustain. As we look to the future, Webb is just the beginning. It will pave the way for next-generation telescopes, designed for direct imaging of Earth-like worlds, capturing actual light from their surfaces instead of relying on transits. But for now, Webb is our greatest hope, our sharpest tool, our bridge between the loneliness of being alone and the wonder of discovering we are not. It represents the best of humanity, curiosity, courage, collaboration, and the relentless drive to explore, no matter how vast the distance or how difficult the challenge. We live in a time when the question, "Are we alone?" may finally be answered within our lifetimes. It might be a faint signal from a world 100 light-years away, a mix of gases that should not exist together, a tiny blip in the infrared spectrum that changes everything we know about the universe. And when that moment comes, it will be because the James Webb Space Telescope pointed toward the stars, read their hidden messages, and brought us one step closer to finding our cosmic neighbors. The universe is infinitely large, infinitely old, and infinitely full of secrets. But with Webb, we have finally built a key that can unlock some of those secrets to find life, to understand our origins, and to realize that we are part of something far grander than we ever imagined. This is the adventure of our generation, and the James Webb Space Telescope is leading the way. Please like, comment, share, and subscribe to the channel.